Okay. Good morning. So this is the first of three labs that we are planning to um, record. So today we will focus on the procedures for simulation. Okay. So we start off generally with this desktop, and then we have to just create one folder so that all our work is inside that folder. Okay, you can give your USN and don't give any spaces because that creates problem later on, and just press enter and the folder will be there just to keep your work inside this folder. That's all. Okay, so double click on the folder and it will be empty to begin with. So in this first experiment, we are going to create the design, the Verilog design, and do the simulation. So I will do the first one. So how do you start creating the design? Right click and then create document empty file, and then this will be created like this. Double click on that and then you can type whatever you want here. Okay, so already I have typed the code for full adder and file save as. Okay, wherever you want to save it inside your folder, I'm calling it full adder .v. Okay, the extension .v is also important, and you can save it and it will get saved over there. And this is the save button. If you do any changes, you can press the save button here also. Okay, so this is the Verilog design. This is text file but the .v extension. These blue lines which start with the double backslash, they are all comments. Okay, and the rest of course is your Verilog code, begin module, end module. So once this is done, then you can minimize this window. Okay, and go back to the folder window. Then you should see your Verilog file here, and here you say right click, open in terminal. Okay, so the terminal will come like this. Yours will be white and black. I just made it little bold so you can see clearly whatever I am typing. So from now onwards, we can start doing the steps for simulation of this design. That is the first. Anytime we have a design, we want to simulate it, meaning we want to see the waveforms for checking the functionality. Okay, once that is verified, then you can go forward for synthesis. So let us try to do the simulation for this design. Okay, so always the first step is CSH. We are changing from the default shell to what is called as the C shell. Okay, and the next step is another command called as source space slash home slash cad slash CSHRC. Okay, what is the meaning of this command? So the Linux operating system, it doesn't come default with the Cadence tools. So after the operating system, we install the Cadence tools, and we have to do this step in Windows. If you install some program, automatically the binary will be added to the list of programs that are there. It will say should I put in program folders, etc. But here we have to specifically tell Linux where all the Cadence tools are being installed, and that is what this single command is doing. Okay, and press enter, and this message is very important. We told in the lab also, if you don't see this message, do not proceed. The rest of the commands will not work. Welcome to Cadence tool suite. So now we are ready to do the simulation, and we are going to use a tool called as Cadence NC Verilog or NC Compiler, and the command is NC launch space minus new. Okay, and press enter, and this window will come. Here click on multi-step and it will ask you some options. We are basically trying to create this cds.lib file in this step. Okay, so that is what we want to do. So click on that and it will ask where, and that it's inside your folder, so that is fine, and just say save. Okay, and then it will say how would you like to configure the cds.lib file, because it doesn't know whether you are going to do VHDL or Verilog or mixed design. But since we know that we are going to work with Verilog, click on the third option and say OK. Okay, and then it will come. And here also, if you see, suddenly the cds.lib file would have been created, and say OK. Okay, so now the file is there, and this is just a library file related to some basic primitives required for Verilog. Okay, because we have chosen Verilog design. So now we are ready to do the simulation. So before we go, the simulation itself is divided into 3 steps. Okay, in the first step, it will check the syntax of our Verilog design. That is, are you giving the statements legal statements? And that is true. I'll just highlight this design, okay, and that is through this first button which says Vlog, and if you see there, it says launch Verilog compiler with correct selection. So compiler is a general statement. There is a C++ compiler, there's a Java compiler, there's a Verilog compiler. Compiler does only one thing, that is check if all the statements are legal in your design. Okay, so that is what we are also going to do here with this step, and you click on that button and you will see some messages below. Okay, here very important, if you get anything in the red color, that means that there is an error. You have written some Verilog statement which is not legal. You have to go and correct that statement. Okay, and once you do that, how do you go and correct the statement? Click on this file again, whatever changes, so it will give you some information about where that particular error is there. So you search for that line in the Verilog file, make the changes that will correct the error, click on save. Okay, and then just come back here and press this button again. You don't have to start the tool and all again. Okay, so once this is completely done without any red messages, that is no errors, then inside this work clip, inside this full add, one module will be created. This would not have been there before. Now only after this compilation it is created. Okay, so if you just click on that single click, you will see that a new button will be highlighted here, and that is called as the launch the elaborator with the current selection. So elaboration is another step in the simulation process where some intermediate format for the design is created. That is, we have the Verilog design, we do the compilation. Okay, but directly we cannot go from compilation to simulation because this is a very simple design, but you could have a Verilog design with thousands of lines in practical designs. So the elaboration step creates a intermediate model of the design, and from that it is going for simulation. So it will create all the modules, the interconnection between the modules, what is the input, what is the output, all those things it will use to create a intermediate design. So we will click on that. Okay, highlight this module and click on the elaborate button. Okay, again no red messages should come. Okay, so generally in elaborate stage red messages will not come, hopefully, if you've done everything correct. So now open this snapshots folder by clicking on this press, and here this new thing would have come. This would not have been there before the module elaborate step. Highlight this. Okay, now this last would have got highlighted, launch the simulator with the current selection. Click on that. So this will launch the actual GUI where we can see the design, and we can also select which signals we want in the design to see the waveform. So this window you can close, double click on the design, you will see all the signals in the design. Let's plot all of them, right? So click inside this window once, single click, select all with Control A, and go to this option which says send the selected objects to waveform window. Click on it. So here you will get all the signals, all have been selected. So first unselect all of them. One by one we are going to give the values and do the simulation. So we need to give the values only for the primary inputs. So according to our design, you see here A, B, C, N. So these are the only ones we need to give the values. The rest will get the values automatically. So right click, okay, go down to simulation and create force. And here you see the module name full add and the signal name dot A, and tick B, it is X currently. You can give it any value, 1 or 0, and say OK. Do it for B. Simulation, create force, full add dot B, so it is a signal B, give it 0. Go to C in, right click, simulation, create force, and then give it 1. Okay, so now we can see the waveforms. Let us give some time. There's a very small button. This button run continue the simulation until the next breakpoint or for the duration entered in the time field. So this number here is the time field. Currently it is set to 10 or 10 nanoseconds. Let us make that 100. Okay, and do the simulation. Press this button. Okay, so it has done the simulation. For anywhere if you click, you will get a red line, and along that line the input and the output values. So 0, I'm sorry, A is 1, B is 0, Cn is 1. So sum should be 0 and carry out should be 1. It is correct according to the functionality of full adder. And intermediate signals, we are plotting them, but we really don't need those values. Okay, let us change it again. Now I want A is 1, let it continue to be 1. I want B also to be 1. So simulation, create force, it is 0. I want it to be 1. Okay, but it is not changing. Why it is not changing? It is not changing because it will change only when we redo the simulation. Remember this message, run slash continue. The first time is run the simulation. The second time you give the new value, you have to continue the simulation. Okay, and how much time to do the simulation? For the duration entered in the time field. So press the button. Okay, again it is not changing. Why it is not changing? It has changed, but we have to move the cursor and go to the new value. So you see it has changed at 100 nanoseconds, because first time we did from 0 to 100. Second time I press this button, it did from 100 to 200. If you go down here, it will be up to 200. And this time you will see A is 0, A is 1, B is also become 1, Cn is 1, and sum is 1, carry out is also 1 according to the functionality of full add. And you can do this any number of times. Okay, only thing is you have to change to the right to see the new values, and you can keep changing and give the values again and again. Okay, so this is the steps for the simulation. Let us see one more design. Let us do the shift register. Okay, so I will close this. So again, something about this cadence, this thing, this is generally for practical or industry level tools. So at a time we can only do one design. So once one design is over, you have to close all the windows. Okay, and we have to start again from NC launch new. So I'll close all the windows. I'll just copy that design. Hold on one second. So I'm going to do the shift register. So I wanted to show how to give the clock signal. I'll copy the design, and here I have a new document. I'll paste it here. Module shift reg input clock input shift input load input tn si output register declaration, and here we have the always block if clear dout equal to, okay, and this should be, we should enter some values. Okay, so its comment is there. So if clear, that is if clear equal to 1, that means that the output should be cleared. Clear generally means you make it 0. Okay, so let us see if that works. Else if load, okay, load means we take the value from the input and give it to the output. So this should be dn. Okay, parallel load. And if it is not clear, if it is not load, then you do the shift. This is the shift operation. Okay, and then we, some extra things have gotten copied, that's fine. Okay, and that's it, end module. So this is the shift register. So let us save it again. File, save as shift reg.v, save it. Okay, so I'll also click once here. Now go back here and I'll just list with ls command, and it should show me my shiftreg.v file. I just created it, right? So now again nc launch new, and don't worry about the this thing. Even though the second design, you create the cds file again, just the default options. It will say already exist, you want to override, say yes and save options. Okay, now I have the new file shiftreg.v. So same procedure: compile, elaborate, simulate. Okay, compile, elaborate, simulate, three separate steps before you see the GUI for the waveform. So first we'll click on this, highlight this design this time, and click on the Vlog button. Okay, Vlog button. So it did the compilation, it didn't give me any errors. So now inside this work lib, okay, I have already done full add before, that is also there, but I don't want that. This time I want the shift reg. So click on shift reg folder and the module. So second step, once you click on the module, this launch elaborator will be highlighted. Click on that, it will do the elaboration. And two modules, I don't want the full add module, that is already done. I want the shift reg module this time. Okay, so shift reg module has come. Double click on that, we see all the designs. So again, click once inside this window, Control A, select all the signals and send the selected objects to the waveform window. So all have come, all are highlighted, unselect them. Okay, now first, this is the first time we are doing clock signal. So clock signal I will show you how to give. Right click, highlight the clock signal, right click and go down again to simulation. Okay, but instead of create force, do the deposit value. Okay, so deposit value, sorry. So now this is basically how we are going to give the clock signal. So the first deposit value, it can be 0, it can be 1. Your clock can start from 0 and go to 1, or it can go from 1 and go to 0. Let us say I start from 0. Okay, deposit the value at time 0. And how to get another option here, click on this line here. Okay, this will give you another option, and if the first one is 0, obviously the second one has to be 1, and this is the amount of time for which it continues to be 0. You can change this if you want. You can change this from 10 to 15 nanoseconds, 15 ns. Okay, and below here there is a button called repeat every. Okay, click on that repeat every and add a time. Okay, what this means is, this is the overall period of the clock signal. Let us say it is 25 nanoseconds. So from 0 till 15, okay, it is going to be 0. From 15 to 25, it is going to be 1. So that is going to be the shape of my clock signal, and say okay. So now let us see if we can get the clock signal. Click on the small button for the time field. Again, I will put 100 and do the simulation. So I see that I am getting the clock signal. So clock signal is coming according to my inputs, right? I have got the clock signal of period 25 nanoseconds. Now let us give the other values. So there is a certain way in which we give the values. You can follow the same way, no problem. Okay, generally first we will clear, okay, and then we will take the value. So I am going to set create force. Okay, let me not use create force, let me use deposit value. So simulation deposit value. Okay, now I'm going to deposit the value 1. Okay, generally when the beginning of the simulation, we will clear the contents. Okay, so at the beginning itself, let clear be 1. okay, and let it be 1 for say some 50 nanoseconds, okay, and after that I will make it 0. So here I am going to make it 0 after 50 nanoseconds, and I will remove this repeat every, okay. I don't want it to repeat like a clock. The beginning of the simulation for 50 nanoseconds, okay, I want the clear to be 1 so that the register's contents are cleared. After that happens, I don't want the clear signal ever to come again, because clear is somewhat like a reset signal, okay. We don't want to be resetting. I just want to clear it once and then let the normal operation happen. So that is what I'm going to do and say okay. Now I will do the simulation, and now you see here, right, up to this point clear is high from 100. Now why it's from 100 is already the simulation had run till 100 nanoseconds. So 100 to 150 clear is high here in this range, okay, and at the first positive edge, and here we see the clock edge coming into the picture. If you see the code for the shift register, whatever happens, okay, it is completely synchronized to the positive edge. Unless the positive edge comes, the shift register output cannot change. But once the positive edge comes, then it will check each of these options. So if any of those options is true, then it will choose that particular branching statement. So here nothing happens here, even though clear goes 1, because this is a negative edge. So it has to wait, and at this particular point the positive edge of the clock comes and it sees that the clear is high. So here it changes the value of the output, clear the output to 0 0, and even though clear goes slow, the output stays at 0 0. Why does the output stay at 0 0? Because the shift register has a memory functionality. Even if the output goes to 0 0, it will store the previous output until at the next clock edge some of these things happen. So after, let us do a load, okay, let us load something into the shift register. Let me put a value 8 hexa. So let me put the value AB, okay, hexadecimal, okay. And then not only that, according to the design, okay, if LD, that is if load, only then the design will take the value that is in DN. So I should also make this high. So I will do the same thing, simulation deposit value. So you deposit this value at 10 nanoseconds, and after that, okay, I'm going to make the load also 0. That is, it will take the value, okay, and then after, say, let me give this a little bigger so that the clock edge comes, otherwise it will never see the value. After 50 nanoseconds you make it 0, okay, and again I will not do repeat every, because I just want to do it one time to take a value and say okay. Now again do the simulation. Until you do the simulation, nothing will happen. That is the first thing. And here also we have done the simulation but nothing has changed. For that we have to take this to the right, okay, you take it to the right, and then here you see AB has come, okay, into the DN, but it has not come to the D out. When will it come to the D out? At the next clock edge, because at the clock edge load is high, and also it sees the value AB in the DN, and AB comes to the D out, okay. So now I have done clear, I have done load. So now let us just let it shift the contents, okay, into the next and so on. So for that, what should I do? So again in the code I should make load 0. That I have done, okay. So now here, for example, it is not loading, it is not clearing, so AB continues to stay at the output D out. So now let me make the shift high, and I should keep it permanently high so that every clock cycle it shifts. Now it will act like a true shift register. So this is the order in which you should do the operations: clear, load, then shift. So let me do the load operation now. So I see the, sorry, shift operation, simulate, okay. Now I can just do a create force, because I don't want it to do anything but continuously be high, so that it continuously shifts for every clock edge, and I press the simulate button. Nothing has changed. Why? It has changed we just have to go where it has changed. Okay, so then go to the end and we see now it is shifting. It starts with AB, then it becomes 52, then A2, phi2, B2 and so on. So if you keep doing this, it will keep changing. Okay, so something has gone wrong. It has gotten um, so I'll check this 1 second. So it should get, it's not getting the correct value, but the 5 is okay, but the Z is not correct because it's getting this thing. So the reason for that is I see that I have not set the shift in signal. So that is what is creating the problem. So let me change this also. Okay, so brown, yellow, all these are not good colors for waveforms. The only colors acceptable in normal operation are green. Okay, so mistake I had done was I have not given the shift in value. Let me create force to 1. Okay, and say okay. So let me do the simulation again. Slowly it will improve. It will not improve instantaneously. Okay, because it's a 4-bit signal, the shift has to come and eventually it will shift into all the bits. Okay, and we see that we are getting FF. So basically after 8 clock cycle edges, okay, 8 clock edges, the 1 has shifted and it has become completely a this thing. So you can continue. You can, now I can make the shift as 0 and make the load as 1. Okay, so I'll make the shift simulation, create force, let me shift. Okay, and then I want to do the load. So now what will it do? It will not shift the value, it will take the here AB. Okay, so it has made shift 0, load 1. So again load AB. So now with Sn equal to 1, let us again go back to shift operation. Simulation, create force. Okay, and load, make it 0. It's not correct to have both. Okay, we cannot be shifting and loading simultaneously. That is that will result in erroneous operation. So now we see the shifting from AB to phi 7, AF, phi F, BF, etc. Okay, so this is the simulation, steps for simulation, and we saw 2 designs, one combination, one sequential. So in the next we will see the steps for the synthesis. Okay, so this we will stop now.